Alright, we're back at it again with this chlorination, and I just wanted to thank everyone just for getting all involved in this project. Actually, it's been really fun sort of chatting science in a way with all the people with the messages and the comments and ideas and stuff for how to improve this synthesis or just subtle things to change. I have a few select ideas I like to highlight that I thought were really good. The YouTube comment from a person called Jane Doe who suggested, just completely different synthesis pathway, starting from methyllacetylene, which is as like a 3-carbon source, and then that's a terrible drawing, but as a 3-carbon source, and that's sort of kind of readily available as map gas. Also, there was another one on my subreddit. If you don't know my subreddit, you should check out r/Explosions&Fire. It's to do with this channel as well, not just Explosions and Fire. From TG Specialist, you can read his post up there. A really interesting pathway as well, sort of well thought out, and a lot of the stuff will definitely work. It's just, and same with the problem with the methylacetylene pathway, it's just heaps and heaps of steps. It might seem like, there's only 8 steps, how long can that take? But, I have to film every step and edit it, and, if it doesn't work, I have to go back and blah, blah, blah. So 1 step a week, really, at maximum pace, and that's, so as soon as there's 8 steps, it's like, I'll be working on nothing but this for the next couple of months. In terms of actually improving the synthesis that we did the other day, where we bubbled chlorine through liquid isobutene, there were a couple of really good suggestions to why it didn't work. And I think a lot of people picked up on the fact that probably having it in the direct sunlight with all the UV was probably causing the radicals to go haywire. That probably meant the reaction didn't work very well. The YouTube comment from Piranha03 something or other, some number, always helpful. He suggests probably the reason it didn't work very well is because of the byproduct, which I didn't think about very much. The byproduct of this reaction is the hydrochloric acid, or HCl gas. If we don't do anything about that, then that can go on to react with our product. And we didn't do anything about it, we just had the DCM, and so that HCl probably reacted with our product either during when we were bubbling the chlorine through or when we were distilling off the DCM when we gave it a bit more heat. So it wasn't at -30, it was at 40 degrees while we're distilling off the DCM. There was a couple of suggestions on how to get rid of the HCl because we don't want to hydrolyze this product. We don't want to put an OH there. So, we don't really want to hastily put in some sodium hydroxide because that could ruin our product, and especially if we're trying to distill it. So there were thoughts that maybe we could put hydroxide in but then just take it out before the distillation. I like Piranha's suggestion of using sodium acetate in the reaction. It wouldn't dissolve very well in the DCM or at all, but it would disperse and react with the hydrochloric acid to form acetic acid and sodium chloride, and that would sort of remove it from the product, and the acetate isn't such a big issue. Obviously, there are actual good bases for this kind of thing, but they're just not available to the home chemist, sort of things like triethylamine, Another suggestion was from a YouTuber called Daniel Coleman, which is really weird. I know a Daniel Coleman in real life, but it's not the same person. And he suggests that we do this reaction, instead of doing it in DCM, we do it in pyridine. And that way the HCl would react with the pyridine. Other people have argued that perhaps pyridine is too nucleophilic and would, instead of the chloride, would react, with our substrate. But I don't think it's that nucleophilic, and it's something I would like to try, and I've tried to order some niacin to make some pyridine. So that's where we're at in terms of suggestions on how to improve this. But I feel like the big issue and the big hindrance for me to start doing this reaction is still the dry ice and doing it at cryogenic temperatures. And I think Jason1, another commenter, got it right when he said, well, why don't you just do it in the gas phase? All the references I've referenced have been about doing this reaction in the gas phase. But that's why we've suddenly got all these issues when we started trying to do it basically in solution. All these side reactions going on that happen in solution but don't happen in the gas phase. So I thought, all right, now fuck it. I don't have any dry ice. Let's just try and do it in the gas phase. This, if you haven't seen it before, is the ideal gas law, and it shows how pressure, volume, temperature, and the number of moles in a substance are related to a reasonable approximation. So in our case, it allows us to work out how many moles of a substance there are at a given pressure, volume, and temperature. So pressure, we know that's just going to be atmospheric pressure, because we're not going to be able to put anything under pressure in this reaction, because that's way out of the scope of stuff I can do safely or easily. We know the temperature because that's just going to be room temperature. And then volume is basically the largest volume of the gas I can collect at once, because we're going to have to make the isobutene first in the reaction as a gas that boils at -8 degrees, and then collect that and then put chlorine into it to chlorinate it later. So the largest container I have is a 2-litre glass container, and then we're going to be able to put maybe 1.5 litres of isobutene in there, and that allows us some, some sort of space in case the chlorine causes it to expand a lot. So we can do the maths. So N equals the pressure is 1, because we're working atmospheres, times by 1.5, because we're working in litres here. Temperature is in Kelvin is 298. That's roughly 20 degrees. And then R is a constant, which changes depending on which units you choose, which allows us to use the unit of atmosphere in here. That doesn't really seem like you should, because it's atmosphere. And in this case, it's 0.082. I don't remember that off the top of my head. Crunch the numbers, we code it out, and it is 0.61. No, there's an extra 0 in there, 0.061. I wish it was 0.61, which is 61 millimoles. The amount of grams of substance that'll fit into 1.5 litres at ordinary atmosphere is 3.5 grams. 3.5 grams. That's the largest scale we can do it at, 3.5 grams, which is the biggest challenge of gas phase reactions, because gases just take up so much space for such little amount of actual molecules. However, in our case, I still think it's worth pursuing, because we're adding such a heavy chlorine to it that if we do it on this scale, our theoretical yield is still 5.5 grams. That's not a trivial amount. It's definitely recoverable. So now I think there's enough chalkboard. We definitely should cross to our setup and have a look at how we're making this and collecting it. All right, and you may also notice that I fixed a frame rate issue I had from last video. Thanks for some people pointing that out. So now the video won't be so sickening to watch. Now, because we're dealing with isobutene as a gas, we can just pipe it as opposed to trying to condense it, which is a lot easier and allows our one pump to pump the reflux condenser, which allows us to reflux this mix here. We have some tertiary butanol and sulfuric acid in there. They phase separate, but I think they've got a very different density. Sulfuric acid is twice the density of it. Still interesting, it phase separates. And then over here, we have a 2-litre container. It's full of water. I managed to invert it and then suck all the air out of it. So we can fill this full of isobutene, well, 3/4 full. Like I said, we want to leave a little bit of water, so that hose will eventually go in there. I'm just letting it because there's a lot of air in this system that we don't really want in here. Oh, I should have said this first, but this whole setup is actually inspired by another video I watched just a couple of days ago by a YouTuber called John Black Super Chemist, and it's in all caps, so I assume I have to just yell it like, John Black Super Chemist. His link is in the description to his channel. You should go subscribe to him and make some good videos, and he did the sort of the same reaction I'm doing here, but with isopropanol. I just added all the tertiary butanol and sulfuric acid together at once because we saw last video they didn't really react that much at room temperature, so that's why I didn't bother with the sort of addition funnel setup, because it just simplifies things a lot, and simple is better. There's of course a way to check if the bubbles coming over are in fact a flammable gas, the alkene that we want, and that's to check if it's flammable or not. Rather than just put a match to the end of the hose here, which I feel isn't very great, what we can do is I've got some soapy water here. Alright, we've actually done it. This here is full, yeah, I'd say it's pretty much right on where we wanted it. I mean, it was very, very slow. It took, you know, 2.5 hours to do that, and I was expecting it to be a lot quicker. In future, what I would do is I'd heat up the sulfuric acid really hot and then drip in the tertiary butanol, now that I have the reflux condenser here, so I don't have to worry about the pot temperature too much. Because I noticed what I could do is I could shut this valve here, which would keep the pressure in the in the line, and then add in some more tertiary butanol, quickly, and then shut it up, open back up the line, and I would get heaps more gas coming through from it. So I said there were some issues with gas phase reactions at home. One of the issues was the fact that the number of moles takes up such a large volume, so even though you have such a large volume, you don't actually have much of your chemical. The other issue is a safety issue, because now we have 1.5 litres of a flammable gas just sitting here. And I mean, gas explosions are very, very powerful, scarily so. It doesn't really help at all that the fact that we have to pump in, an aggressive oxidizer like chlorine. Worst case scenario here is a very bad scenario. I don't think it should blow up. Otherwise, I'm doing it, so, I'm obviously believe that I'm going to be able to survive today. It's something to always think about. All right, I do have a rule. It's a very common sense rule that there is no chlorine to be done inside the lab. It all should be done outside. However, it's nearly night time and I want to get this done, so I'm going to break the rule. And I'll be all right. I'll be all right. That's not really the attitude to have, but I'll manage. We've got about 5 grams of TCCA in there, which is just under what is needed. Oh, no, it's 4.5 grams, sorry. So according to my calculation, we need 4.7 grams of TCCA to completely chlorinate all the isobutene, assuming we have 1.5 litres, which is, a reasonable approximation. So we've got 4.5 because we don't want to over-chlorinate it, and I'd rather it works to a little extent than we get too greedy and it doesn't work. We've got some dilute hydrochloric acid. This time we don't actually need to dry the chlorine, so we're not running it through any calcium chloride or anything like that, because as you can see, the gas is above a whole lot of water, so it'll be so full of water vapor anyway that it's a waste of time to scrub out any water vapor. The chlorine outlet is just in some sodium carbonate solution, and that'll just scrub it out, because we want the apparatus to be full of chlorine before we start putting any in there, because otherwise we'll just be pumping air into there. That'll be wasted space, which we don't want. Oh, also, the note is that we're not scrubbing out the HCl. Remember last time this was giving us problems. So 2 reasons is the fact that, we're in the gas phase now, so hopefully it won't matter too much. And also, being above the water is a big advantage in the fact that that's going to pull the HCl out of the gas, because the HCl is such an affinity for water. Not going to bubble the chlorine through the water before it gets to the reaction mix, but the HCl, any HCl in there will be pulled out of it. Also, another side point, you may have noticed I'm using this sort of tubing which won't stand up to the chlorine. I usually use the Teflon tubing, but there's just no way I can get a Teflon tube up into here and then down and then connected there. There's just, my brain, has been thinking about geometry for ages, but there's just no way I think I can get these curves to line up so that it'll work. So we're just going to have to sacrifice this bit of tubing, but it's sacrificing itself to science, and that's what it wanted, so. Alright, we pumped quite a bit of chlorine in there, and there's something along all the sides here. It could just be water vapor, but maybe perhaps not. You can see a sort of a film on top of the water there. Some of the stuff that's escaped. That happened when I had to pull the hose out to put it back in the scrubber. So now the hard part is, how do we get the stuff out without it just going everywhere? My thought is perhaps, there's just a little bit of water left in here, and I'll put a lid on that. I don't have a good fitting lid or something on there, but I get a lid and then I can put it on there and then just invert it, and we can have a look at it all. But this is where the system really breaks down. Shit. Oh, yeah, okay, I'll try that. Alright, here we are the next day, and it looks very positive because it looks cloudy, but that's actually just because I've added a whole lot of salt to try and salt something out. There's really nothing there. What's really missing is the smell of the methyl chloride, because I'm sure that's what we got last time, the real sharp, eye-watering smell. What's there is still the smell of the hydrocarbon, sort of garlicky, butane-y kind of smell, which is what you get when you just do the elimination of the tertiary butanol. So, for whatever reason, I really don't think the chlorination took place, and the only thing I can think of is that we just didn't put enough chlorine into the flask. I actually ended up putting more TCCA in at the end because I just thought we had to use quite a bit of chlorine to, you know, purge this sort of apparatus. But I don't know, it just didn't seem to chlorinate. We're just going to do it again, except this time we're going to put the addition funnel here with a Kleisen adapter. And we'll just do it again, except this time we won't try and worry about any stoichiometry with the chlorine. We're just going to pump a whole heap in and see if that changes anything like that. Alright, it's been going pretty well. I'm getting pretty good at producing this isobutene now. But we're going to do a new thing, slightly different thing. Not because I think it's a particularly good idea, but because if I don't, everyone will finish watching this video and think, well, what happens if we just put both hoses into the thing at the same time? So we're going to put both hoses in from the chlorine outlet and the isobutene outlet. The chlorine is going to be much more rapidly generated than the isobutene, just because the isobutene is very slow, whereas the chlorine can just, you know, pump over at a sensationally fast rate. I don't have two addition funnels, pressure equalizing addition funnels. I did at one point have two pressure equalizing addition funnels, but I happened to drop one on the concrete floor, which is very, very unforgiving to these glass bits, and it took me a while to sweep it up. So that was a sad moment. So I'm going to just have to add the chunks of TCCA directly to the flask. Quite a bit of isobutene to start with anyway, so it's not going to be a chlorine excess, hopefully. And also it'll ruin both sets of tubing, but, you know, more sacrifices. It's fine. Alright, it's genuinely working. I can see a liquid kind of forming, especially around the chlorine outlet. And also, it was getting very warm, and where that hose was hitting the glass was like too hot to touch, very, very hot. So that's, I didn't realize it would get quite so hot. I knew it was exothermic, but I thought, it'll be alright. But I might put some ice in the water. That'll help things all round, and we don't really want to overheat, especially seeing as I can't really stop it. I've just realized. I realized it was hot, and I thought, I better cool it down. I better, like, you know, stop the chlorine and let it cool down. And I thought, I can't really stop the chlorine very easily, short of disconnecting it and letting it vent into the air around the lab. So this is a very poor design, and feel free to insult me in the comments for this decision. It's 2 days in a row I've violated one of the lab's basic rules, which is no chlorine inside. You know, we're going to try and enforce it in future. I don't know why it didn't work last time, but it's seeming this continuous setup seems to be a little bit better, or maybe we're just actually getting chlorine into the system now, and before we weren't. An interesting development. So a lot of the methyl chloride, well, it has been floating on the top. Sorry, I'm trying to get the light here so you can see, floating on the top of the liquid. However, just quickly, see that big white section? That's actually not on top of the liquid. That's sort of sitting in the like the curve of the flask, and some of it's actually run out all the way down to the bottom. Just see it down there, that milky white substance. So, I mean, the density greater than water is a bad sign, because that implies overchlorination, because methyl chloride should be less dense than water, but only just. It's about 0.98. So, you know, slight things can cause it to, you know, the very slight amount of overchlorination, you know, all the organic liquids will dissolve in each other and it'll sink. So it's bad, but it does actually allow us to retrieve the material down the bottom there fairly easily, a lot more easily than we can obtain all the stuff in the rest of here. So as the stuff sinks, perhaps we'll be able to collect it, and I'll collect some of it now. Alright, here's the stuff that's sunk. Quite a bit of it. Look how much there is. And it smells bad. Alright, and here's the result from all our hard work. It's about 4.5 grams, well, I mean 4 grams of methyl chloride. It weighs in at 4.5 grams, but there's still a tiny bit of water, so that's why it's over a whole heap of sieves, because I don't really want it to break down anymore. You can see that lump of water there, you know. I don't want it to do any hydrolysis or anything like that. So overnight I'm going to wrap this up in a couple of Ziploc bags and put it in the freezer, the Ziploc bags, so it doesn't smell. And then we'll wait into the morning, we'll revisit this and work out how to either, distill it or check the boiling point. Ideally we want to distill it, but it is hard to distill things with such a small amount of liquid. The good news is that our product at 63 degrees should be the lowest boiling point thing. The issue last time as well, because we had so much DCM, is that by the time we boiled off all the DCM, we started causing all these other reactions to occur. I could be making that up because it's only really 40 degrees. It's only, 20 degrees above room temperature, but at least this sort of solvent-free method allows us to just distill off, our product first. We also have a little bit more product. It was just sort of how I separated it out from a lot of the water, but there's still a little bit of the white product at the bottom there and here as well. If the distillation works, then we might try and extract the rest of this with DCM and get just a little bit more. So here's our product before distillation. It's really dwarfed by the 50ml flask, but they're the smallest flasks I have, because if you go any smaller than a 50ml flask with the same joint size, I mean, they're just ridiculous at that point. And I don't really want to go to different joint sizes because I generally don't do real small scale chemistry, but here we are. It does smell pretty bad. It's not like an awful, sickening smell, but it's like sweet and it's kind of similar to last time, but less sharp. But the ultimate test really here is boiling point. We're just going to do hot water bath and then just lead it through this system here into an ice flask here, flask on ice, because we'll lose all of this like with the condenser setup, whereas hopefully with this we have less mechanical losses through the system. I've managed to get all the water out of there. You can see it's just one layer. Well, the worst fears are confirmed. Looking so positive once again, but this water is 82 degrees and it's not boiling, and it should boil at 62. So what we have here once again is not methyl chloride. So back to the drawing board. I can say that because I'm actually drawing on a board. I have a drawing anyway. I guess we're going to have to really determine a boiling point of this in order to work out what's gone wrong. Alright, everything's cooling down on another failed attempt. The thing boils at about 150 to 160 degrees. You did actually get some that boiled over, but once again, I don't really know what went wrong. The important thing is we can't really blame UV this time as much, because I did the chlorination at night time inside and I distilled it inside without heaps of direct sunlight. That's not really getting heaps of sunlight in it. And there wasn't even a slight bit of boiling at 60 degrees. Absolutely nothing. And it was in the dark all night. Yeah, I'll have to explore some other methods. I do like the pyridine one. I also like making this chlorosuccinimide. I've got some stuff for that on the way. So I think we'll try and make succinimide just because that looks like a fun reaction. Yeah, difficult, but I hope you enjoyed this anyway. I mean, we reacted two gases together to form a liquid, and we've done that. We just don't know what the liquid is. It would be great if I still had access to NMR, because then I could just run an NMR of this. The stuff distilling over has a reasonably consistent boiling point. It's the same product we made the other day. If we ran an NMR, I feel like it would be pretty clean, but I don't really have access to that at the moment. So the mystery continues. Well, I don't know what we'll do next, but we might do something completely different because I'm a bit sick of this at the moment. Just something completely random. But yes, I hope you enjoyed it, and thanks for watching.